Hi viewers, welcome to another session of All Force e-learning program. Right, today we are going to learn about Coulomb's law, its properties, applications and limitations. Talking about Coulomb's law, before going to Coulomb's law, let's have a review of what we have learned yesterday, the previous video. Now I was telling you charge is a fundamental property of matter which is responsible for a special force called electric force. So earlier people observed a special force between matter which was stronger than the gravitational force. It was different from the gravitational force. The gravitational force between two masses is a feeble force, weak force. But people observed a strong interaction between two bodies. So for this special force there may be a special property and they termed it as charge. So electric force between two bodies, they named it as electrostatic clinch. Electrostatic clinch is the force of attraction which binds them together. Electrostatic clinch is due to the charge there. Unlike mass, mass as stated by Sir Isaac Newton, gravitational force is of only one type, attraction. Gravitational clinch, it's of only one type, there is attraction. Mass, all matter is of only one type. But the electrostatic clinch or electric force, they have observed of two types. There are two types of forces. For example, let me tell you. Let us have a small demonstration. Consider, we have studied electrification. The process of giving charge to a body is called electrification. I have explained various methods, right? Charging by friction, charging by conduction, charging by induction. And one more point to note is, charge always appears in pairs. You can never produce single charge. When you give charge to another body, let us say positive charge, this body giving, the body that is giving gets negative charge. Equal and opposite. Charge always appears in pairs. You can never produce a single charge. So charge is produced. Electrification, the first process, when I produce charge by friction. So in friction we have studied, consider two bodies, put them in contact, move relatively. Friction, due to friction, electrons migrate from one body to another body. One body gets positive charge, other body gets negative charge. So in this process, let's suppose a glass rod, when rubbed to a silk cloth, right? A glass rod rubbed to a silk cloth is suspended by means of a string. So this gets positive charge. Now consider another glass rod rubbed to another silk cloth and again suspended near to this, like this. Let's say this glass rod gets positive charge. Now when I get these two close, they move apart. They are separated. Force of separation, right? Pushing force of separation, pushing apart. Now this they named it as force of repulsion. Later, similarly, suppose in second one, instead of glass rod, the first one is glass rubbed with silk suspended by a string. Instead of glass rod, if I get a ebonite rod rubbed with woolen cloth, right? When I suspend the ebonite rod, right, this negative, when I bring it closer to it, both get stuck up. They attract, come closer. Approaching force, they approach, they come closer. Attraction, clinch. So thus people noticed the two type of electrostatic forces. One is force of separation, other one is force of attraction. First one, glass rod and glass rod, two similar bodies. When I rub a glass rod with a silk cloth, whatever nature of charge that it gets, in another glass rod rubbed with silk must get the same nature of charge. So two similar charges. When two similar charges were brought together, they move apart, separate. Force of separation, pushing force moving apart, force of repulsion. So similar charges separate, repel like charges repel, similar separate like repel. So similar charges are separating one another, so like charges repel. Now when I get an ebonite rod gets an different charge. So glass rod and ebonite rod, this is glass and this is ebonite rod, and this two get attracted, move towards, come closer, approach, force of approach, electrostatic clinch. This is called force of attraction. So people noticed there are two types of electrostatic forces: force of separation and force of approach, force of repulsion and force of attraction. Now people thought, intuited, when there are two types of forces existing, then there must exist two different types of charges. Thus people came to a conclusion that there are two types of charges, different nature, named as positive and negative. Right? So that way force has led to the separation of two charges like this. So first, forces, electrostatic force. Electrostatic force are of two types. Unlike mass, all mass is of same nature. There is only one type of force, a gravitational clinch. It's gravitational force of attraction as stated by Newton. But electrostatic force are of two types, force of attraction and force of repulsion. So in first case, when I was charging by conduction, when charged by friction, now two bodies when charged by friction put together and moved relatively, one gets positive, one gets negative. Now these two attract one another. So charging by friction leads to attraction. Charging by friction precedes attraction. A simple example, when you rub your hand to the handle of a chair, plastic chair, you rub a hand to the handle of plastic chair, then you notice the hair getting attracted towards. Rubbing the hand, friction, charge is produced. Now the hair gets attracted towards the chair. So charging by friction precedes attraction. There is attraction. Unlike charges are produced, so they attract one another. Like charges repel, unlike charges attract. Similar charges separate, get separated. Opposite charges attract. Unlike attract, similar separate. So you please remember such. This is a simple memory tip by which you can remember, right? Similar separate and unlike attract. Opposite attract. Similarly, I have given the same thing in the previous video also. A small tip to memorize which body gets what type of charge. You have to remember such type of tricks you have to use so that you can remember this without confusion. You can write the things under any condition while writing the entrance there. You get confidence. So first case, charged by friction. Whenever charged by friction, then after being charged by friction, they attract. So charging by friction precedes attraction. Right? First case. Second, when I charge by conduction, when charged by conduction, when bodies are charged by conduction. So I was telling you in the previous video, consider a already existing charged body and this is connected to another conductor. Right? This charge is shared. You know, in charging by conduction process, similar charge is being transferred, shared. The same charge, a positively charged body, now when in contact with another conductor, same positive charge is shared. So when you consider charging by conduction, right, already existing positive charge, another one, when you put in contact, same nature of charge is being transferred. Right? Now there are like charges. There after conduction, they repel. So charging by conduction leads to repulsion, or charging by condition precedes repulsive force, repulsion. Charging by conduction precedes repulsion. For this, I'll give a simple example. Suppose, unfortunately, if any person gets in contact with an electric plug, whatever it is, right? Please don't try it, but at home. But unfortunately, let's say a person gets in contact with a plug there. So when you get in touch with it, in contact, a similar charge is given to you. Now, after getting charge, you are thrown away. You are repelled away, right? So when like charge, when you get in contact, then similar charge is given, then you are pushed away, separated charges, similar charges get separated, separate repulsion. So whenever you charge by conduction, similar charge is given, and this similar charge after being charged, they get separated. So conduction precedes repulsion. Third one, suppose when I charge a body, when a body is charged by induction, when you charge a body by induction, induction, affecting something without contact, right? So I was explaining in the previous video, when a charged body put in very close, nearer to a body, then unlike charge is deposited to the nearer end and the like charge to the other end. Now these two opposite charges deposited to the near end, these two unlike charges, this leads to attraction. Induction, so whenever charge is induced, opposite charge is being induced. When opposite charge is induced, now this leads to attraction. So induction leads to attraction, or induction precedes attraction. Opposite charge is induced, unlike charge. So unlike charge, attract. Opposite, attract. So when opposite charge is induced, there is attraction. For this simple example, when you move very close to a TV screen, a switched on TV, when you switch on the TV and when you move very close to the TV screen, that TV screen behaves as a plain charged sheet. So when you go close, just very near to it, then your hair gets attracted towards it. You being induced by the charge, the TV screen behaves as a plain charged sheet. Now that induces charge on you, your hair gets pulled, attracted. So charging by induction leads to attraction, or induction precedes attraction. But one point you have to understand. So if by three methods, whenever you give charge, so charge is being given to a body, then after being charged, either the bodies are attracted or repelled. Now this two types of forces. For this, the analytical approach of this force is given by Mr. Coulomb, right? Charles Coulomb has given the analytical formula for the force between two charges. The force between two charges, if I consider two charges Q1 and Q2 separated by a distance r, then force directly proportional to Q1 Q2 by r square. But before going to it, Coulomb's law is applied under certain conditions. Coulomb's law is not applicable to all types of charges. Let's say whenever you charge a body by induction, now when you induce, when charge is induced, the induced charge is spread over the body. Now there Coulomb force you cannot calculate. Coulomb force is applicable only for point-sized bodies. Point-sized bodies, point charges. What do you mean point charge? The size of the charged body when compared to the distance of separation. The size of the charged body when the size, radius of the charged body, distance of separation d, when r is very much less than d, then the charge can be considered to be a point charge. So point charge, for point charges only this law is applicable. Now what happens if it is not a point charge? If it is a big charge conducting sphere, then how do you apply? So luckily, whenever a big charged sphere is considered, a big charged sphere, when charge is uniformly distributed for a conducting sphere, then the center of all the charge lies at the center of the charged sphere. The center of the charge coincides with the center of the sphere. So you can assume all the charge is concentrated here. This is called center of charge. Similar as center of mass. So when charge, all the charge that is lying on the surface, all can be imagined to exist at the center. Similarly, another charge conducting, big conducting sphere, where the charge is uniformly spread over the surface, you can imagine all the charge is being concentrated at the center. Now imagining all this as point charge and all this as point charge, now these two behave as point charges. Now the distance between their centers, you have to consider the distance between the charges, distance between the centers, right? So the line joining the center. The distance d, r, it is the distance between the point where the charge is concentrated and this point where the charge is concentrated. So distance between the centers, right? This is the reason the force is inversely force between 2 point charges. When I consider charge, all the charge is said to be concentrated at the center of charge. Even for this also, distance between them is r. Then the force F is directly proportional to, so force proportional to the product of the charges, and it is inversely proportional to square of the distance between the charges there. Now if I remove the proportionality, F is equal to small k naught q1 q2 by r square. So this is Coulomb's force. Now this constant is called Coulomb's constant, k naught. K naught depends on this k naught, small k naught. It depends on the system of units you consider, the system of units of all the quantities what you consider, and it also depends on the medium that is the medium that is present between the charges. It depends on the system of units what you consider and the medium that is present between the charges. Based on this, the constant k naught is defined. In various systems, force is defined as F is, in various system of units, force differs. CJ system, k naught is 1. In SI system, k naught is given as 1 by 4 pi epsilon. In SI system, k naught is given as 1 by 4 pi epsilon. Now epsilon is defined as epsilon. It is the constant, it is the constant of a medium which defines the extent to which it affects the force between the charges. It is the parameter which defines the extent to which it affects the force between the charges there. Epsilon, permittivity of the medium. And so 1 by 4 pi epsilon, k naught is equal. So when I substitute, so force F is equal to 1 by 4 pi epsilon q1 q2 by r square. So now let's talk about the applications of Coulomb's law. Applications of Coulomb's law. First one. So we were learning about Coulomb's law. Coulomb's force F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Now this is the mathematical form of Coulomb's law. Mathematically, Coulomb's law F is defined as F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Right? So when I consider air as a medium, then this value F is equal to 9 into 10 power 9 q1 q2 by r square. So when air is considered as a medium, air vacuum free space, then force F is equal to 9 into 10 power 9 q1 q2 by r square. A first very simple question. If an electron and proton are separated, proton are separated by a distance of, let us say, 3 centimeter. An electron and a proton are separated by a distance of 3 centimeter, then what would be the electrostatic force between them? Electrostatic force between them. So we know charge of electron or charge of proton, right? The magnitude is 1.6 into 10 power minus 19 coulombs. Distance d, 3, given in centimeters, please convert into meters. Whenever you substitute the values in a formula, you have to see that all the things are taken in the same system of units. So distance d is 3 is 10 power minus 2 meters. Now force F. So substituting in the formula, F is equal to 9 into 10 power 9 into charge of proton 1.6 into 10 power minus 19 into charge of electron 1.6 into 10 power minus 19 by distance 3 into 10 power minus 2 whole square. So force F is 9 into 10 power 9, 1.6 into 1.6, it's 2.56 into 10 power minus 38 by 9 times 10 power minus 4. So 9 gets cancelled. So force F is equal to 2.56 into 10 power minus 38 9 goes up, minus 9 when it goes up it is plus 9, minus 4 when it goes up it is plus 4, 9 plus 4 it is 13, so plus 13, or force F is 2.56 into 10 to the power of minus, it is 25 newtons. So an electron proton separated by a distance of 3 centimeter will attract with a force F is equal to 2.56 into minus 25 newtons. A simple problem based on this. Now let us go a bit deep inside. Now second question. Suppose when you consider two charged bodies Q each separated by a distance d, the force of repulsion between them F is equal to 1 by 4 pi epsilon q1 q2 by d square, or substituting for them, now the force is 1 by 4 pi epsilon q square by d square. Question 1. Now what happens to the force between the charge when the distance between them is either doubled or halved? So suppose if the distance between the charges is doubled, then what would be the new force? When the distance is doubled, the new distance is 2d. So plus q here, now this is moved there. The new force F dash is equal to 1 by 4 pi epsilon naught q into q by, the new separation between them is 2d whole square. So therefore this is 2 dividing 2 by 1, so performing 2 by 1, F dash by F is 1 by 4 pi epsilon naught q square by 2d whole square is 4d square by F is 1 by 4 pi epsilon q square by d square. So q square cancel, d square cancel, it is 1 by 4. So the new force when the distance is doubled, the new force F dash by F is 1 by 4. So F dash becomes F by 4. So when the distance is doubled, force becomes F by 4. What happens to the force when the distance is tripled? Had it been tripled, then distance is 3d square. So it is 9, 3 square by 9. So F dash by F will be 1 by 9. So F dash is F by 9, 3 square. What will happen if the distance is made 4 times? Right, 4, 1 by 4 square, 16. So if the distance is changed n times, d dash is n into d. If the distance between two charges is changed 2 n times, then the new force F dash would be F by n square. When the distance between the charges is changed to n times d, then F dash is F by n square. Force decreases n square times. When distance is doubled, 2 square 4. Distance tripled, 3 square 9. Distance made 4 times, 4 square 16. So when the distance is changed n times, force becomes F by n square. Similarly, so what will be the force between the charges had the distance between them being halved? If I halve the distance between the charges, if the distance between the charges is halved, now the charge is brought to this point. Distance is halved, d by 2. New force F double dash. So it's 1 by 4 pi epsilon naught q square by d by 2 whole square. So initially when they were at a distance d, force F is 1 by 4 pi epsilon naught q square by d square. Now the distance is halved, the new distance is d by 2, F double dash. So this is equation 1, equation 2. Dividing 2 by 1, F double dash by F. It's 1 by 4 pi epsilon naught q square by d by 2 whole square. It is d square by 4. By 1 by 4 pi epsilon naught, it's q square by d square. So this cancel, q square cancel. F double dash by F is 1 by this by 1 by this moves up. So it is d square by 4. It's d square by 4. 4 moves up. So F double dash is 4 times F. It is 4 times F. So whenever the distance is halved, the new force will be 4 times F. Now if he asks you what happens if the distance is made 1/3. If it is made 1/3, d by 3, then it is d by 3 whole square, right? D by 3 whole square, d square by 9. Then it is d square by 9, 9 times. Force becomes 9 times. If the distance is made d by 4, 16 times. So if the distance now is made d by n times, if the distance between two charges is reduced to d by n of the initial distance is d, now the distance is reduced to 1 by nth of the initial distance, then the new force F double dash is, it is n square F. See, when the distance is halved, d by 2, it's 2 square, 4. D by 3, 3 square, 9. 4 square, 16, right? So, F double dash will be n square times F. So, when the distance is changed to d by n times, distance is changed to d by n, then the new force F double dash is n square F. This is the second. So, just now I have explained, when the distance is made n times d, third point. So first formula, first problem what we have done is, when the distance is increased to n times, force becomes F dash is F by n. So when the distance is increased to n times, d dash is nd, then F dash is equal to initial force F by n square. First. In the second case we have studied, when the distance is made to d by n, then force F double dash is n square times F. Now the question is, there were two charges at a distance d, right? Now the distance between them is doubled, first case. Later the distance is halved. So first the distance is made 2d and later it is made half. Then what would be the ratio of the initial force to final force? So that is, if initially the charges were at a distance d, two charges q and q were at a distance d, now the force is F. First, then if the distance is made n times t, force becomes F by n square. Next case, second case, if the distance is made d to d, it is decreased to d by n, then force F double dash is n square F. Now he is asking you to compare when the distance is increased to n times to the force when the distance is reduced by n times. Distance increased to n times, distance decreased to n times. So F dash is F by n square and F double dash is n square F. So dividing this cancels. So F dash by F double dash is 1 by n power 4. So the force F dash is F double dash by n power 4. That is, two charges initially are at a distance d. Now when the distance is made n times d, nd, the force is F dash. Now the distance is now made to, it is reduced to d by n. Second case, the force is F dash, F double dash. Then F dash is F double dash by n power 4. First, when distance is increased to n times, it is F dash. Second case, when distance is reduced to n times, then the force is F double dash. Then F dash is F double dash by n power 4. Or F double dash is n power 4 F. Right? There are three things we have learned in this one. First, initially two charges are at a distance d. The force between them is F. Now the distance between them is doubled. When you double the distance, then force becomes 1/4. When you double the distance, force is 1/4. Tripled, 1/9. 4 times 1/16. N times, when you increase the distance n times, force becomes F by n square times. Second case, when the two charges are at a distance d, now the distance between them is halved. When I halve the distance, then the force becomes 4 times, 2 square times. If I reduce the distance to 1/3, d by 3, then it will be 9 times. Reduce the distance to 1/4, then it is 16 times. If I reduce the distance to 1 by nth of the initial distance, then the force is n square times F. When you reduce it, right? So next, Now combining these two problems together, now application, multiple application question. Now there are, first where the distance is double he'll be asking you, then when distance is half, then he's going to club both and he's going to ask the question. So initially charges are at a distance d, so the final entrance question would be like this, right? Initially the charges are at a distance d, then in first case the distance is made n times. In the second case, the distance is reduced to d by n. Then, what is the ratio of the force in the first case to second force? In recent years, there was an entrance question asked based on this one, right? So, when the distance is increased n times, then f dash is f by n square. Then the distance is reduced by n times, f double dash is n square f. Then initial force to final force. Force in the first case to force in the second case. So f dash is f double dash by n power 4, or f double dash is n power 4 f dash. A very important problem to note, right?